Hello. I realize I'm not your normal professor, but he will be joining us shortly. Today is an introduction to the normal distribution and the standard normal distribution. What is the normal distribution, you may ask? The normal distribution is a fundamental concept in statistics and probability theory. It is characterized by its symmetrical bell-shaped curve, which describes how data points are distributed around the mean. What are the key characteristics of the normal distribution? The first one is symmetry. The normal distribution is perfectly symmetrical about its mean. This implies that the left half of the distribution is a mirror image to the right half. The next key characteristic is a bell-shaped curve. The bell-shaped curve of the normal distribution indicates that most of the data points cluster around the mean, with fewer and fewer points appearing as you move farther away. The spread of the normal distribution is determined by its standard deviation, a measure of how spread out the data points are from the mean. The normal distribution is widely used in various domains due to its properties. In manufacturing and quality control, the normal distribution helps in monitoring processes. The normal distribution is crucial in finance and economics for modeling asset prices, returns, and risk. In summary, the normal distribution is a cornerstone of statistics and probability. By grasping the fundamentals of the normal distribution, one can unlock deeper insights into the patterns and probabilities that govern the world around us. Thank you, and now here's Dale.
Hello folks, I hope you're feeling normal because we're going to talk about the normal distributions and the standard normal distribution. First thing to notice is how I describe those. The normal distributions, because there are lots of them. The standard normal distribution, there's only one. You might even think of it as the golden standard normal distribution. With that said, you can see the sections we're going to cover after that pretty much except for this last one. 5.5 we will not bother with, and if you really care, you can stop by the office and I'll tell you why. And here are a couple of things we're going to do, including interpreting graphs, because we're going to look at normal probability distributions, and we're going to find areas under that golden standard normal curve. So here we go. We're going to be talking about continuous random variables. Remember what they are? The discrete ones are where you can count them. For example, in this number line, you see you can count 1, first, second, third, fourth, and so on. Even if you don't come to the end, even if you're out here at 1,250 or let's say 60, you can still count them. However, with continuous ones, there's an infinite number of values, even between 0 and 1 or 0 and 3. Those are continuous, remember now? And we're going to talk about a probability distribution of a continuous random variable. So, continuous probability distribution. We're talking about a random variable x, so we're talking about some kind of characteristic. And the most important is the normal one. And you're going to be using that part of your calculator, for example, many, many times. The graph is called a normal curve. You might have heard of that, or if not, maybe you've heard of the bell curve. Well, that's sort of sloppy, but you'll see some better ones. That's the basic idea. There's a much better picture. Notice this center line, just to give you a heads up, that's the axis of symmetry, because you can twist along that line and end up with the same thing. The right and the left-hand sides are mirror images of each other. Another thing to remember is the mean, median, and mode, even though they're usually different. With the normal distribution, a normal distribution of any kind, they're all right in the center. The mean, the median, and the mode. Usually all we'll care about is the mean, which is right here. But remember, because at this point, you have the most number of whatever this number is, it's also the mode. And you can sort of forget about the median for the time being. So it's bell-shaped, as I mentioned before, and you've got that symmetry about the mean. Here's the axis of symmetry. Let's give that an S. The total area. Here's another one. Total area under the curve. So if you had a bucket of paint, how much paint would you need to paint all this area under the curve? Well, you might think of it as one bucket of paint. The total area is 1. 1 what? Well, actually, it doesn't have any units. It's just a 1. Notice on the left and the right, it looks as though the curve comes to an end. However, that's misleading, because whether on the right or on the left, that curve continues indefinitely, or you might say to infinity. And also keep in mind, this curve is always above that x-axis. So even though it might get very, very close when you come out here, for example, that curve still, oops, sorry about that, that curve still does not touch the x-axis. A couple of other things to remember. Remember, this is a normal curve in general. There's mean right in the middle. Now you've got some other interesting things. We've talked about standard deviations, and going from that center point right here, if you go to the right or to the left exactly 1 standard deviation, there are 2 special points. These are called inflection points. Now, lots of curves have inflection points. For this particular one, what you're interested in mostly is the fact that if you start at the top of the curve, at the apex of the curve, if you like, and go either right, in this case, you're going steeper and steeper and steeper. Imagine running down this or riding a bicycle down this. It keeps getting steeper and steeper. That's dangerous, right? Well, this inflection point is where things start changing. If you look carefully, it starts leveling off. It starts leveling off. It never levels off totally. In the other direction, the same thing happens. It gets steeper and steeper and steeper until it gets to the other inflection point, at which case, that point, it starts to level off. Those are the inflection points. We'll not talk about that too often, but that's just something that can connect you with some of your algebra background. Now, just temporarily, we'll talk about the discrete probability distribution. That can be graphed with a histogram. You're familiar with some of those. Remember, they look something like this. I'm not going to draw much of one, but this might get your memory going. Something like that along an x-axis. And if you're lucky, it might resemble a little bit of a normal curve, although it isn't. That's for discrete ones because you've got these bars or sort of chunks of rectangles. For the continuous ones, that you don't have those chunks. You can't count these, for example. If you did, for some reason, want to graph those, you could use a function inside called normal PDF. However, even though on that particular menu that we'll talk about soon, this is actually the first option at the top. 1, normal PDF. But you only use that normal PDF for graphing. You're probably not going to use it at all in this entire semester. Now the probability density function, that's what the PDF stands for, has 2 requirements. First of all, the area under the curve is equal to 1. Does that sound familiar? Mentioned that before. The function can never be negative. That means it never touches or crosses the x-axis. Remember those two. Very important. Next. Now we're talking about any normal distribution. A normal distribution, not the, a normal distribution could have any mean at all and any positive standard deviation. So take a small note here. The mean could be negative. Positive, 0, could be any of those. But the standard deviation will always be a positive number. The mean, the first one, will tell you the location of the line of symmetry. In other words, I'm going to give you some like chicken scratching here. You might have this normal distribution. The mean, remember, is right in the center for this first normal distribution. And you might have another one further to the right. This normal distribution, we'll call this distribution 2, as its mean right in the center, but notice they're left or right of each other. And this one over here could be in the negative range. If the x value here, for example, is 0, and this normal distribution would have a negative mean, and the one on the right here would have a positive mean. The standard deviation, the second number we're talking about, describes how it's spread out. If you look closely at these, you'll notice that even from my chicken scratching, you can tell that they're pretty much spread out the same. It almost might look as though I took this one and just moved it to the right to get the second normal distribution. So the mean tells you the location of the line of symmetry. That means left to right. And the standard deviation tells you how spread out it is. In other words, think of it this way. Here's your normal bell curve, perhaps. And if I grab a hold of these two ends with my hands and pull to the sides, I could end up with something looking like that because I've stretched it out. This one would have a greater standard deviation, a larger one. If I did the opposite, if I took these two handholds and pushed them together and ended up with something like this, all squeezed together, that wouldn't have much of a standard deviation. It would have a small but positive standard deviation. Here are some examples right here. So we'll take this example A, take a look at it. That's sort of our starting point in this case. Notice the inflection points. And the mean for this one is a 3.5 right there. And the standard deviation, or where this goes out about 1.5 in both directions. That's where the inflection point hits. Now, let's take a look at B. There we go. Now for this one, notice we've got the same mean. So its location of the axis of symmetry is at the same place. However, the standard deviation is smaller, which means it doesn't have as much spread. That means it's squished together, so to speak. That's B. Over here it's C. There are inflection points. Now on this one, the standard deviation, notice, is the same as for curve B. So it's spread out or squeezed together the same amount. However, the mean is not the same as for B. It's a smaller number, so this B curve is moved further to the left by 2 units if you pay attention, because this one has a mean of 3.5, this one has 1.5, so we've moved 2 units to the left. Now, let's try some experimentation for you. Let's try and see if you can figure this out. Here's where, as I've said before, hit pause. Yes, I don't mind that. Hit pause, see if you can answer the question, and then come back. All right, you're back. I hope you tried. Which one has the greater mean? Remember, the mean is where it is, left to right. So which one is further to the right? Greater means like greater number. Which one's further to the right? Remember, we're talking about the axis of symmetry. And which one is further to the right? Obviously, curve A. You get that right? Hope you did. Next, another possibility. See if you can get this one right. If you missed on the last one, here's your second chance. Which one of these curves has the greater standard deviation? We're not talking about the mean, we're talking about the standard deviation, which is its spread. Which one of these is spread out more? Okay, are you back? B. It's spread out more than the A, which is squished together. Got that? Now let's get to some real numbers. We're talking about some test scores for New York State on a grade 6 mathematics test. Notice, first of all, and this is very important, what do we know about that curve? Because what we know about that curve is going to lead us in one direction or the other, or a third or a fourth direction. They're normally distributed, so you've got this bell-shaped curve. Notice the symmetry. You could fold it on itself. The normal curve shown below has this distribution. What's the mean test score? Where is that? It's at the axis of symmetry, or where you could fold it on itself to get a mirror image. Over that, you go to the top, and you just move straight down like this. And there's your axis of symmetry, and it also tells you what the score is for the mean. In this case, 600 is the mean. So we'll throw this up here. Estimate the standard deviation. Okay, this is a lot trickier though. Remember, the standard deviation happens at the point of inflection. So we'll go up here to the peak and we'll slide down to the right. Now notice it gets steeper and steeper. Where do you think it starts to level off? Oh, I'm just as challenged as you are on this one. I'm going to guess somewhere around here. Now, if I am correct about that, then I could be a little bit off, but this is just practice. Where did that happen? I go straight down. Where is this? Well, there's 600. Over here, 640. So this is about 620. And if I look on the left, because maybe I work better on the left, go down steeper, 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 and somewhere in here, it starts to level off. And that looks like about 580 on the x-axis. So it looks as though the standard deviation might be about 20. And we've got that standard deviation extending in both directions. Now, to be honest, I've seen this slide before, but don't worry about being off, thinking it's 15 or 19 or 18 or 21, just to get the idea. That's all we care about. So here's a summary of all that. We have a normal curve. We've got the symmetry. The mean is where it folds on itself. This is the way I think about it. And we can guesstimate that it's about 600. Now, maybe it's 599, or maybe it's 602. We don't really care. It's the idea. And notice, because of my prior knowledge, I did happen to hit the 20 on the button for the standard deviation. That's where the inflection points are. Now, a little bit more and a little bit of review here again, too. Remember the empirical rule. We talked about this earlier. Remember about the empirical rule. So right over here on the right. If you remember about the empirical rule, we were talking about 1 standard deviation, 2 standard deviations, 3 standard deviations. What about them? Well, if you go 1 standard deviation both ways, you're going to cover, this should sound familiar, about 68% of all the data. Well, what about 2 standard deviations both ways? And that would cover about 95% of the data. And 3 standard deviations, this one's a little bit harder maybe to remember, but it covers almost everything. There are almost no data items beyond 3 standard deviations in either direction. So there's our summary. For this particular example where we had the mean at 600 and the standard deviation was 20, 68% was from there to there. 2 standard deviations, 95%. Remember, that's from the center or the mean out here and out to here. All of the area between those 2 points encompasses 95% of whatever we're interested in. It might be people, it might be Venetian blinds, it could be anything really. And last of all, if we go out 3 standard deviations, that's a long ways. Notice that 3 standard deviations takes us way out here. And if you take a look, what do you think we have for an area beyond that? Now, if you look at it carefully, it's hard to see anything between the curve and the x-axis. In fact, because we're using a physical pencil or pen, we can't even see any area, even though some does exist. Same thing on the other side. Area under this curve, there's not much there. Okay, now we get to that standard normal distribution. Remember, there's only one. And if you want to think of it as the gold standard in a way, just to keep it distinct from any normal distribution, here we go. The standard normal distribution is a special one, a particular one. This one has a mean of 0. That means the x values hit 0 right there. And the standard deviation is 1 unit away in both directions. So the standard deviation goes out to +1 and to -1. Remember again, keep hitting on this because we'll use it a lot. The area under the curve, exactly 1. You might wish at times to think of as 100% because it means the whole thing. If you were painting this, for example, you'd have to use a whole gallon of paint, perhaps. Whatever works. Okay, now we've got something very special and a little bit new. For this standard normal distribution, we work with something called z-scores. And each of these z's corresponds to a standard deviation. So if we start in the middle at the mean, go left 1 z, that's 1 standard deviation. Go, oops, did I say left? I mean right. If you go right another standard deviation, you're at a z-score of 2 and a z-score of 3, and so on. There is no end to the z-scores. Somewhere out here you might have a z of 7,208, way out there. And they extend in the other direction. Remember, a z of 0 is right in the middle, very important. And out here, this z is -1, z -2, z -3. Got it? How do we figure out the z's if we don't have that curve? Well, here's the formula for you. And this is what it means. To get a z-score, first of all, you're interested in some particular value. And we just call that x because it'll vary from one time to the next. And we're going to take whatever that number is, we're going to subtract what the mean is for this normal distribution. And to make it a standard one, we'll divide it by the standard deviation for this normal curve. You got that? So, and some of these things I know I'm repeating, but I want to make sure you don't have a chance to forget it. So the standard normal distribution has a mean of 0 and a standard deviation of 1. Alias, z-score of 1. The area under the curve, 100%. This is the standard normal distribution with 2 lines under the standard. Now, in the past, in the not too distant past, this standard normal distribution was even more important than it might seem right now. Because what people would do, statisticians and students alike, would be to take whatever normal curve they had and convert it to the standard normal distribution. Because we know a lot of things about the standard normal distribution. We can do a lot of tricks with it. So if we can take our normal distribution, and if we can pair it up in some way with the standard one, anything we can do with the standard, we can do with ours as well. Now, you won't understand this right away, I'm sure, unless you've taken statistics before, but you'll get this eventually. In fact, you might want to, at the end of this chapter, you might want to go back and watch some of this again. All right. Some of this might seem obvious at this point, and some of it might not. Now this is down here the standard normal distribution, or golden standard if you want to think of it that way. Now remember, each of these z-scores, like this z of -1, this z of 3, the further you go out either direction, there's not much area left under the curve. So if this were a physical place and you started walking from the axis of symmetry or the center or the mean, if you go out here far enough and you're painting under the curve, once you get out here to about 3.49, you can just about put your paintbrush away. You won't see much of anything to paint back here. And the same thing happens if we go in the other direction in the afternoon. Once you get about here, about 3.5 or 3.49, there's almost no area under the curve. So for all practical purposes, you probably don't need to do any more painting. So the cumulative area increases as the z-scores increase. Now, what do I mean by cumulative area? This is very important because whether you're using tables or other technology, almost all of those, when we're talking about area, starts looking at the area from the very left-hand side. So if we get rid of this guy in here, to paint the cumulative area, we'll start out here sort of at negative infinity. And here's our paintbrush, if you can imagine that. You'll have to use your imagination. When we start painting with the paintbrush, that area or cumulative area, we're going to start painting here. Well, the calculator or table or whatever you use starts way out here to the left. So if you're talking about the cumulative area for a z of -1, that means everything up until that particular point. Starting out at the left, the far left, 1,000,000 miles, 1 mile, whatever you want to think of it, you go until you get to the certain stopping point that you're talking about. We'll get back to that again. Remember, these are z-scores, but it still works the same way if you think about the mean compared with other x-scores. Some tips. Cumulative area for z equals 0. Where is z equals 0? Right in the center at the mean. Now what's the cumulative area? Well, that means what's all of the area until you get to that center point. Well, since it is symmetric, the right side and the left side has the same area. So this left side encompasses 50%, and the right side has 50%. So the area, remember the total area is 1 for the entire area under the normal curve. If you only go to 0.5, it's going to have half of that one area. For the z-score is close to 3.49. Remember, that's way out here. And by the time you get to 3.49, you've passed almost all the area. There's almost nothing left. So you're extremely close to the total of 1. Now, let's have some fun. We want the cumulative area that corresponds to a z-score of 1.15. First of all, as I'm going to say many, many times, the first thing you do is draw a picture. What picture? It's going to be your normal curve. You don't have to be good at drawing it, just to give you an idea. Now, we're talking about z-scores, so right away we can say, oh, z-scores, there's 0 right in the middle. Okay, we're talking about a z-score of 1.15, so it's not to the left of that, it's over here to the right, 1.15. And we're talking about cumulative area, so it's everything up until you get to that 1.15. I'm going to draw that picture again so we can see more of it. There's our 0 in the center, and we had the 1.15 out here. What would be the area up to 1.15? You can see a lot of space in here if you can see my pointer. Remember, if we get up to here, that's 50% or 0.5 of the area. We're going beyond that. So the area, the cumulative area up to that is going to be more than 0.500. So whether you use a table or whether you use your calculator, when you get what you think is your answer, make sure it's over 0.5. There's your picture, and there's your area. There's the 1.15 to the right of 0, of course. And the area, again, of course, is not only more than 0.5, it's a lot more than 0.5. But remember, it can't go over 1. To do that calculation, it would be nice if we didn't have to add little pieces. Oh, that would be terrible. But there is a simple way of doing it. Grab your TI 83 or 84. We're going to say you have TI 84 because most do. What you need is to get to the distribution menu. On your calculator, you're going to see DISTR above one of the keys. To get to it, you're going to hit that second button on the upper left of your keyboard, and then you're going to go to the middle right and see a key that's marked VARS. It has a second function, and if you look closely, the second function for that key is the distribution menu, and that's how you get there. Second VARS, and that'll get you to that distribution menu. Now, write this down red or whatever you need to do. It's not hard for me to do it in red, right? But item number 1 on that menu says normal PDF. Remember I talked about that? You use it for graphing, but we won't be using it at all. Make sure you don't accidentally hit enter when you get to that menu. That'll give you normal PDF. What you want is hit a 2 because you want normal CDF. It's the cumulative density function. Cumulative. You want this guy. Now, once you're there, and I'm going to give the instructions in case someone has a TI-83. If you have a TI-83, this is what you'll need to do. As soon as you hit the 2 to get the normal CDF, on your screen, you'll see normal CDF and in left parentheses. Now, if you have the TI-84, follow along because you actually get a menu, so it's easier for you. Now, with the TI-83, you're going to have 4 parameters. That means four numbers or options that you need to put in. The first one is the lower bound, LB, lower bound. That's going to be where you want the calculator to start adding up the area. The second parameter or option is called UB, or the upper bound. That is where you want the calculator to stop and add up everything that it's accumulated up to that point. So think of the lower bound as being the start and the upper bound being the end. So what we need is we want everything up to 1.15. So when I'm at the distribution menu, I'll make sure I hit number 2 to get CDF. For the lower bound, well, if you look at this picture, there's a picture again. The picture says there isn't any lower bound. Well, another way of saying that is it's like negative infinity. So we want negative infinity there. I'll come back to that in a moment. And our upper bound is we want it to stop putting it together at 1.15. Now I said there were 4 parameters, and I've only put 2 in. There are 2 more because remember I said there were many, many, many normal distributions. If it's not the standard normal distribution, we have to tell it what the mean and standard deviation is for our normal curve. So the third option is the mean, and the fourth option is the standard deviation. Now, before we leave here, notice we were talking about z-scores. That means we're talking about the standard normal distribution. So we've got a special condition here. That means this mean is 0, and it means the standard deviation is a 1. So you'll have negative infinity, you'll have 1.15, you'll have a 0, and you'll have a 1. Now, what about that negative infinity? Well, let me clear the board here so it's not quite so messy. There we go. So we want this normal CDF. So let's start almost at the center. I'm going to go to second bars to get to the distribution menu. I'll pick up number 2, which is normal CDF. Now, what do I put in? Well, negative infinity, you have a couple of options. The first option is to simulate negative infinity. You can put in negative 1 start again, negative 1 E 99. And that looks weird. First of all, what does this mean? It means negative 1 times 10 to the 99th power. That is pretty big, and it's negative. So for all our purposes, for all intents and purposes, this is negative infinity. But I have a tip for you. If you don't like putting this in, one way I do it, which makes the typing easy, is I just type negative 9999. In fact, maybe I'll put 5 nines in, just to make it a very big negative number compared to that 0 that's in the center. So if you look at this curve, negative 9999 would be several miles in the left-hand direction. So we're good. And then we'll put the other numbers in. We want it to stop at 1.15. Because this is z-score, we put 0 and 1. And then you're ready to hit the enter key and you'll get your answer. Now, one other thing I need to tell you, because someone else might do it differently, or you might accidentally do it differently and get the right answer. If, when you're doing this, you go to Normal CDF, if you happen to put negative 99999 like me, because it's easy to type, and you put that upper bound as 1.15, what if you forget to put in the 0 and the 1? Well, sort of the good news is if you forget to put in the 0 and the 1, the calculator is going to put them in for you. It figures if you didn't put them in, you are talking about the standard normal distribution. It'll take care of you. There's only one catch. If you start leaving off the mean and standard deviation, you might forget later on. If you're not talking about the standard normal distribution, then you're going to have something in for the mean and the standard deviation. So my strong suggestion is, even when we're talking about z-scores and the standard normal distribution, get in the habit of putting the mean and the standard deviation in anyway. That way, when you work with other ones, you're going to put something in and you won't make a silly mistake. Okay. And the area, we've already talked about that. If you look at the picture up here, the picture is so important. It's more than half, which means that 0.8749 for an area makes sense. By the way, you notice we have a picture here on the bottom of what your calculator screen is going to look like if you're using the TI-84 Plus. If you happen to be using the TI Nspire by any chance, you will find that all you have to do is remember, go to the calculator word page, notice a scratch pad, one of the scratch pads, and the second thing you need to remember is menu. If you can remember those two and you don't know how to get these areas, in all likelihood, just by going to those two, you're going to find your way to the answer. Yeah, you might not believe it now, but you'll find that's true. That's why I like that calculator so much. Okay, we've got another one to try. This is a good reason to pause the video right here and try it yourself, and then come back. Welcome back. I hope you've tried it. So what I'm going to do now is I'm going to say, I'm pretending like it's my question and I never tried it before. How do I do it? Oh, cumulative area, that's everything from the left. And I want it up to a z-score of negative 0.24. So here's my picture. 0 is in the center. Where's the negative 0.24? Well, to the left of it. So somewhere like this is negative 0.24. Our cumulative area is going to be everything to the left. I guess I can shade this in. Now notice right off the bat, this is not as much as half. It's going to be less than half. Less than half. So if you have gotten your results from the table or from your calculator and it's not less than 0.5, you've made a mistake. Go back and try again. So how's it go? Normal CDF, How did I get there? Second bars gets me there. I want number 2. I don't want to accidentally use PDF. I want to put in 4 numbers. We want everything up to negative 0.24. So my 4 parameters will be the lower bound is negative infinity. And if you're following what I do, I'll put negative 9.9999. For the upper bound, I'll put in negative 0.24. And then for the mean, since this is z-score up here, that means that I'm going to put a 0 in. And for the standard deviation, this is the golden standard normal distribution. So that will be a 1. So there's the picture. Do the calculation. And from this note, remember, because it's the z-score, you don't need to put in the 0, 1, but I think it's a safe thing to do. Even your calculator puts it in even though you didn't enter it. Notice that the area is a little bit less than 0.5, so I know I'm in the good region. So if anyone made a mistake, maybe it was the calculator. If it does though, get a new one, or borrow one. And there's my area. Okay, so wrap up. Sketch the normal curve, shade the area that you're looking for. Number 2, find the area by following the directions for each of the cases. Your picture means you need normal CDF, negative infinity, 1.23. And by looking at your picture, you can tell that it's going to be greater than 50%. And the area indeed is 0.8907, pretty much what you expected. Okay, now all of those were areas to the left because that's the way the calculator works. That's the way the tables actually work as well. And many of the other applications most likely do as well. However, on this one, we're going to do something a little bit differently. On this one, we want the area to the right of the Z. To the right. So, grab our picture. Remember, 0 is in the middle. Why? Because we're talking about z-scores. So 0 is in the middle. Where is 1.23? 1.23 will be somewhere out here. However, remember what we're trying to find. We're trying to find the area to the right. So shade this in. This is what you're trying to find. Now remember, the area under the curve is 1 or 1%. If you look at this, this is less than half because to the right of 1.23. So keep that in mind. So when you get your answer, it needs to be less than that 0.5. So normal CDF, this time 1.23 is your lower bound, and your infinity is the upper bound. And I've got a trick there for you too. The way I put it in, because it works, when I get to normal CDF, I'll put in the 1.23 because that's the lower bound. And because I like to make the typing easier, I'll just put a bunch of 9s there. And since I want to be careful and get a good habit, I'm going to put in the 0 and 1. And take a look at that. I better end up with something less than 0.5. So there's my picture. A better picture, I admit. The area under the curve, 0.1093 approximately. We're in good shape. Okay, let's try something different. What if we want the area between two z-scores? Well, remember, the first parameter is the lower bound. Second parameter is the upper bound. And since we're talking about z-scores, we'll put the 0 in and the 1 in just to keep our habits in the right range. There's our picture. Now, I can't really tell exactly whether it's going to be above or below 0.5, but it's going to be a fair amount. So I don't expect it to be too small. I don't expect it to be too big. That's about the best we can do. The area between the two scores. Here's our setup. Negative 0.75, that's the lower bound. 1.23, the upper bound. 0 because it's the z-score. 1 because it's the z-score. And there's the area. And sure enough, it is over 0.5, but not too far over. Use your common sense for this. All right. So we want the area this time. And we're still talking about the standard normal curve. So we're talking about z's. So first of all, I'm going to draw the picture. And 0's in the center. And the z I'm interested in is negative 0.99. So it's going to be over here somewhere. And I want the area to the left of that, which means I'm going to paint the area in here. Well, I want that area. Well, that's good news because we're going to start at negative infinity, and that's the way the calculator likes to work anyway. And the tables and other ones. So enter negative infinity, and you know what I do, right? Negative 99999, because I know that simulates negative infinity. Remember, your other option, easy option, is putting this in. If you want to see how to do that, it'd be better if you just came into the office and I could show you in less than a minute, really. You might like what I'm doing now, but that's up to you. So you want everything up to negative 0.99. This is the upper bound. Where do we stop the area? Right there. We don't have to put the 0 and 1 in, but it's probably a good idea. And this gives you an area of 0.1611. And this should make sense. It's left of the center. So it's going to be less than 0.5, and that's definitely less than 0.5. Okay, can you do this? Hit pause. See if you can do it yourself. We want the area under the curve. See you in a moment. All right, you're back. One more one for the road, right? So draw a picture. Set it again, right? I'm talking about z's. So 0's in the middle. I'm talking about 1.06. So that's over here to the right, 1.06. I want the area to the right of that. So I'm going to go to second bars to get to the distribution menu. I'll hit the number 2. That's all you have to do. And that will give you the normal CDF that you need. And since you want to start it, notice this to the right is Z. So you want it to start at 1.06. So that's the lower bound. Where do we stop? We don't stop. So we'll just simulate positive infinity by just putting a bunch of 9s in there. It's easy to type. We're talking about Z's. So I'll slide my 0 and 1 in there. And I'm ready to go. And there's my area. Notice from the picture, you can tell that it's going to be less than 0.5, and there you go. You know you're in good shape. You want to try one more? Sure, why not? Hit the pause button after I show it to you. Give it a try. All right, take a pause. Come on back. Okay, you're back. What do we do first? Draw that curve. Doesn't have to be terrific. Zeros in the middle because we're talking about z's. We'll have others later, but we're sticking with z's for the time being to make it easy. Now, where do we want to go? We want to start at negative 1.5. That'll be over here somewhere. We don't care, just we want a pictorial representation. And we want to go to 1.25, which will be over here, 1.25, positive. And we want what's between those two, so we can shade that area in on our curve or our picture, and we can see that we're going to look at that area. We know from the picture where we're going to start, where we're going to stop. So where am I going to go? You got this? I'm going to go to second bars. I'm going to pick out number 2, normal CDF. Where does it start? Negative 1.5. Where do we want to stop? 1.25. We're talking about z's, so we're still putting a 0 and a 1 in here. And we don't know exactly how big or how small that is, but we might think it's in the wild vicinity of 0.5. We'll find out. In fact, there is a sneaky way you can, well, maybe not. Let's go to the calculator. We're familiar with it now. You can do that. So draw that picture. There's your picture. Now, ignore this. This is what you would have to do if you're using tables. You don't have to use tables. All you need to know is from the picture again, there's the lower bound. Here's the upper bound. Since we're talking about z's, and we'll use the mean of 0, standard deviation of 1, and that's what your entry should look like. Hopefully, you put the 0 and the 1 there just to keep in a good habit. This is what it should look like in your calculator, and we're in good shape. All right, I hope you got through here and you learned a whole lot. If you have any questions, stop by the office for answers or bring your questions to class. Take care.